we are now in this part of the course we are looking at 3D NOESY HSQC, and we started looking at how the correlations are obtained in the last class. So you can see here this is typically how the spectrum is shown. Here you can see these are the different correlations that we obtain in the NOESY. So this is along the T1 dimension, which is basically the vertical dimension shown here T1. Then you have carbon along T2, that is this horizontal going into the plane of the board, and T3 is the proton. So that means for every given carbon proton pair you will see a set of correlations along the F1 or T1 axis. Okay. So in this particular example what we saw, it is basically in the same molecule. So all atoms are correlated to all the atoms. So IJK here is correlated to I. Similarly, IJK is again correlated to J, and IJK are also correlated to CK and HK. So you can see if you look at these three correlations, all the three. So you see all the three peaks here for HI-CI pair, you see all the three correlations for HJ-CG pair and all the correlations for HK-CK. So now if you look at this F3, F1, F3, F2 plane, sorry, this should be a correction here, this is F2. So if you look at the F2, F3 combination, that is HI-CI, HJ-CJ and HK-CK, they represent nothing but the HSQC. So HSQC is the F2, F3 plane, and that forms the basal plane, that is the basal projection, and on the third dimension we see the correlation. So this is what we saw here, this is how the NOESY HSQC looks like. So you have a 3D spectrum, the base is the HSQC, and this HSQC can be either proton nitrogen or it can be carbon proton HSQC. And for every peak in the HSQC, if you go in the third dimension, you will see a set of peaks or correlations, and these peaks are the one which could come from the same amino acid, or it could come from a far away amino acid, or it could come from a neighboring amino acid. So which is which peak we do not know unless we know the assignment, means unless we know the chemical shift of each and every peak to what atom it belongs in the protein, we will not be able to identify which peak is what type of correlation. Is it intra amino acid, means is it within the amino acid, or is it outside the amino acid? Those kind of information can be obtained only if we have the full complete assignment of every peak with us. That is why I emphasized earlier also, and now I repeat that resonance assignment in proteins is a very important step, without which we can't do much in NMR. So let us move further now. So what I showed you earlier was an example of within the amino acid correlations, but NOESY is not about that. In NOESY we want to see correlations from a far away proton. So for example, consider this case. So the same molecule which we saw earlier, but now imagine that this K, this proton K is coming close in distance to another proton far away N, far away meaning in the sequence, not in space. In space it is close, but in sequence it is far. So this is what we want to capture in a NOESY experiment. We want to get the long range interaction. Long range meaning the distance is not long, but they are not directly connected, they are very far away in terms of the amino acid sequence. So you can see these two atoms are very close in space. So let us see how the correlations will come. So now I can show you, so what we can imagine, that this amino acid is going like this, there is a chain and it come back to this N. Okay. So this is just a schematic drawing to indicate that there is a long chain which is also shown here, and it comes, this atom N comes close to this K. So now when I excite the first pulse in the NOESY HSQC, if you recall the pulse sequence, the first pulse will excite all the protons including this far away, does not matter because all are protons. Now when we do the mixing, this is where the important point comes. When we do the NOESY mixing, this mixing will now take place, that means they will transfer magnetization or polarization to each other, but they will transfer only to those which are close by. So here we saw that HK and HJ and HK are close, so they transfer to each other, But now let us say that this far away atom Hn is close or near only the Hk. Okay. So, imagine that it is near only to Hk and somehow it is not coming close to Hj and Hi. So, in such a scenario it will transfer polarization only to K. Okay. So, there will not be any transfer of polarization from N to J and I. Okay. So, they may look near in this picture, but imagine that they are not close. So, that means only N to K transfer or K to N, again remember it is both vice each equal and opposite or vice mutual. So, both transfer to each other. So, now when we do this inept like earlier we saw, there now we will also get the chemical shift of Cn, because all the carbons will be excited and then they will correlate to their proton, directly attached proton. So, this top part, this part was same as earlier. Now, I have added an extra because now we have an atom which is far away. So, like this there could be many far away atoms, I am just giving an example. So, therefore, in our correlations which we saw, now we can add one more set of correlations you see here. So, here it is coming as Hn, Hn means not the amide Hn, this Hn which is along T1 excited because this is coming from here, then it gets correlated to Cn and Hn, this Cn and Hn. So, this combination is called the diagonal peak. We saw this in the last class. And now, we are getting an extra correlation which is between K, that is Hk and Hn. Why is that coming? Because Hk transferred the magnetization to Hn and Hn was labeled with Cn and Hn. So, Hk was in the T1 axis, here this Hk got transferred during mixing to this, and during T2 and T3 got frequency labeled with the carbon and proton. So, this is extra correlation and this is called a cross peak. Now, this Hk will also, Hn will also come here, because as I told you this is a mutual equal and opposite. This is if Hn transfer to Hk, Hk transfers to Hn. So, in this case Hn correlation is also noticed in this part of the spectrum, where we are detecting Hi, sorry, it should be coming here. So, let me correct this here, it will be here. Okay, because it gets correlated to this. Hn is correlated to Hk, Ck, and Hk is correlated to Hn, Cn, mutual, equal and opposite. So, this is a new correlation which we are going to see now because of this far away atom coming close to Hk. So, let us see in terms of a spectrum what happens. So, these are the correlations, again I have to, I will make this correction, this goes from here, it comes here. Okay. So, now if you look at the 3D planes, now we have added one more plane, if you notice here blue color, and that is Cn, because now we have an extra Cn Hn combination. So, this Cn Hn combination is shown here. Okay. And now, in that plane along the Hn, that is along Hn along T3, you will see along T1 Hn and Hk along T1 or F1. So, along T1 or F1 along here we see these two peaks. So, one of them is Hk and one of them is Hn. So, one which is the Hn here will be called as a diagonal peak, because it will be repeating Hn here plus Hn along this axis, Hn along this axis. So, it will become a double diagonal peak. I mean it is repeated 2 times, so it is a diagonal peak. Now, if you look at this plane here, that is the Hk Ck combinations, I am looking at here Hk Ck Hk plane. In the Ck Hk plane along the Hk, that is along T1, you will see now I am observing an extra peak Hn coming from this combination Hn, this chemical shift correlation. So, this is a new chemical shift correlation which I am now getting because of the NOE effect, which was earlier not present because we were only considering within the amino acid. So, this is a very important correlation for us, because it is giving us a distance information. Remember, every peak in a NOESY corresponds to a distance. So, every peak gives us information about the proximity. So, therefore, this peak shown here in red color, although the color wise in a real spectrum they will all be the same, but just to highlight I have shown it in a different color. So, please do not think that the color of a peak changes for a nosy peak, it is all the same. So, the Hn correlation now to Hk is giving us a distance information between these two atoms Hn and Hk. So, that is basically the essential or unique or a very beautiful idea about nosy, that it gives me correlation, chemical shift correlation between far away protons. I mean far away in the sense far away in the sequence of amino acids, but near in the space. So, this is what is shown here. So, now let us look at more carefully in this strip plot manner. So, this is the 3D nosy spectrum which I told you earlier. So, now suppose I take a strip out of this here. So, I consider this strip which is shown in a magnified zoomed manner. Now, here I am seeing here HI-CI correlations, right. So, this is HC combination, but for any given I, some proton I and Ci plane, now I am drawing a strip along this axis. Now, here you can see many different correlations or peaks. So, there could many of them could be the same proton, means from same amino acid, sorry. So, they could come from the same amino acid I. So, Hi, Hj, Hk are coming from the amino acid, same amino acid, and then we have some extra peaks here, and these extra peaks could be a long range or a nosy interaction. This is also nosy, all are nosy peaks here, but these three are coming from the could be from the same amino acid, and these could be from a neighboring amino acid or could be a far away amino acid. So, here you can see what is shown in the bracket is the 3 chemical shift correlation. So, here Hk is correlated with Hi, which is here, and Ci because we are at the Ci plane, we are cutting at the Ci plane here. Okay. So, we are looking at the Hi-Ci plane. So, Hi-Ci is common to all because we are all in the Hi-Ci plane, but along this axis it is changing because of different chemical shifts along this. So, now let us see what could be these two peaks. So, let us say this is some a proton I call arbitrary, I call it H1, so HN1, so HN1 and HI-CI combination, and this could be HN2 some other proton HN2 HI-CI. So, as I mentioned in a structural in a nosy we have proteins have 3-dimensional structure. So, that means suppose this is one amino acid here and it is going like this and then coming back and then there is another amino. So, it is possible that this Hi is close to these protons. Okay. So, if they are close to these two protons, Hi will show a correlation to these protons in a nosy spectrum, but in a J coupled or toxic spectrum we will not see that because they are far away, okay, far away in terms of the sequence. So, now here these 3 correlations as I said could be from the same amino acid, and when the correlations between two protons if they belong to the same amino acid, we use the word self NOE, self means the same amino acid. Now, this H1 N1 HN1, let us say imagine suppose this is the next amino acid mean neighboring amino acid. So, we can say this is a neighboring amino acid and there is a interaction because they are close by in space. So, this could be this is called as a sequential NOE, sequential means the previous or the neighboring. We had also used the word sequential earlier in assignment. Now, this peak which you are seeing here could be a far away amino acid and it is again showing an interaction with Hi because it is close in space. Remember the word close makes a big difference, it has to be proximal, but sequence wise it is very far. So, there is no question of any J coupling between the two. So, this correlation what we are seeing is coming because of distance through space interaction. So, this is how we interpret the nosy. What we do is we cut out strips in a computer like this, and for every HI-CI and could be any of these HI-CI could be any 2 carbon proton. Of course, we should know what they are, which amino acid it is. So, that is why we need the assignments, and if you go to any particular amino acid HI-CI plane, in that we start looking at all the correlations along this axis, and then we try to identify what each peak or each correlation which atom it corresponds to in the protein. That means again I should know that this peak belongs to HN2 and HN2 is what which amino acid, I should know that also, and that again comes from assignment. So, basically the bottom line is we should have assignments of all the peaks in the spectrum. That is why the assignment is given so much of importance. In fact, there is a journal dedicated to NMR assignments. So, if you have a protein which is like about 100 amino acid or more, you could actually assign that protein including backbone and side chain and then publish it in a journal. So, you see that is why the assignment on its own for any protein is publishable, and therefore, it because it requires lot of work and it is very important in the whole process of structure determination. So, now once we have got these peaks, what do we do next? We have got the correlations in the nosy and we have identified that this peak is this is this and so on. So, now how do we convert this into distance? Because remember each peak, as I mentioned, encodes the distance between protons. So, which distance in this case, for example, let us take this peak here, it gives me distance between Hj and Hi, which is I am sitting on the Hi. So, between every two protons, so look at this combination here, between Hj and Hi I am getting a distance. Now, look at this here, this is Hi to Hi. Now, what is Hi to Hi? There is no concept of distance, there is not zero distance, there is no distance at all. So, we do not consider diagonal peak at all. This is what I have been telling earlier also, the diagonal peaks are of no use in a NMR experiment, be it nosy, be it toxy, be it cozy and so on, because they do not show any new information, they are only correlating the same atom to the same atom. But now here between Hj and Hi I am getting a peak, and the intensity of this, that is the volume, the area of this peak will give me information of distance between Hj and Hi. Similarly, for this peak I will get the distance information between K and I, N1 and I here, and between N2 and I here. So, therefore, each peak is carrying a lot of valuable information for me, it gives me distance. So, basically that is what we do, we look at all possible correlations between proton and proton in a nosy, and then all those correlations, that is the peaks, are then converted into distances. So, let us see now how do we classify the different correlations. So, number one is, suppose I see a correlation in nosy between the proton like this and a proton in the same amino acid. So, this is an amino acid called alanine. In that alanine I am seeing between the alpha proton and the beta proton. So, this is, as I said, it is called self NOE or intra-residue NOE. This is not so important for us because the distances do not normally vary, they are fixed distances. So, this is not such a important correlation for us, but it is always there in the spectrum. Now, this let us say I am seeing a correlation or a NOE cross peak between this beta proton of this alanine and this beta proton of this serine. So, this is an amino acid called serine. So, this correlation is now a sequential NOE because it is between neighboring amino acid. This is also slightly important, although not very important for us, because if you take a protein, be it alpha helix, random coil or in a beta sheet conformation, the sequential means this neighboring distance normally is in a fixed range, okay. So, about 3.5, 3 to 3.5, and you would not expect a big difference based on the structure. So, sequential NOE again are not so critical, but it is again present in the spectrum, we have to identify them and assign them. A third category is medium range. Here the distance between the amino acid from here to here is 2 to 4 amino acid separation. Remember, each NH here is one amino acid. So, I can draw a line here and that will become one amino acid. So, you can see there is a separation about 2 to 3, means more than 2, 1 if it is 1 it is sequential. So, but more than 2 and around up to 4. So, these are interesting NOEs because they give us information on the secondary structure. For example, I will show you in the next few slides, if you want to know it is a helix or a beta sheet, it helps us to know that information. We need to know the medium range NOE, medium range correlations in the nosy, and from there we can identify the secondary structure, not the tertiary. For tertiary structure, what you need is this, you need a long range NOE. You need a NOE between some proton like this and some other far away proton like this, which is, you can see there is a long chain here. So, this is called a long range NOE. For example, in a beta sheet, you see this amino acid is going like this and taking a turn and coming back. So, for example, if I have 2 atoms here, this distance will be this will be less than 5 angstrom, but you see they are long range NOE, because there will be 1 amino acid, 2, 3, 4 like this, and this will be about 10 amino acid in separation. So, that called long range NOE. So, the long range NOEs are very important. They are the one actually which tell us the distance, because finally we want to fold a protein. Protein has to be folded in a structure, and for folding you need to bring 2 far away amino acids, 2 or more far away amino acid close to each other, and that will come information we will get from the nosy. So, the more the number of NOEs, better will be the resolution of the structure. Means if I get more and more like this information, correlations, long range, medium range, sequential, the more information I get, the better the structure will come out, because I will have more information to build a model. So, remember again in the last class I mentioned the NOE NMR structure determination is basically a model building approach. We are building a model, a picture. We do not have really the real structure with us, we do not know the real structure, we just build a model which will fit all the distance information that we give. Okay. So, that is how it is done. So, coming back to this nosy correlation plot which I showed earlier, we can actually convert this into distances. So, this is what is shown here. We integrate, meaning we calculate the area of the, or volume of the peaks. The volumes are calculated by integration. Integration can be done in a software, is very straightforward to integrate the cross peaks, and basically which means calculate the volume. Now, volume, as I said, each peak gives me the distance information. So, HICI correlation peak, for example, here this one gives me distance between HK and HI, or correlation between HA and HK and HI. So, as I said, the medium range. So, how do we get the information of a secondary structure from the medium range NOEs? So, you can see here, for example, in alpha helix like this, the amino acids will turn and come like this. So, there is expected to these distances become lesser than 5 angstrom. So, you can see from I to I plus 4, there could be a cross peak between the residue I and I plus 4 amino acid, because the distance between those two will be less. So, these are the different characteristic NOEs which are known to tell us whether it is alpha helix or not. For example, N means HN, the amide proton. So, if I get a correlation between amide proton of residue I with amide proton of residue I plus 3 in a nosy spectrum, that means that particular set 2 residues are in a alpha helical geometry or conformation. Similarly, if the alpha proton of ith residue gives me a correlation to the amide proton of the I plus 3 residue, then that correlation is a signature of alpha helix. So, these are from 4 different correlations which are shown here, are very important to identify alpha helical part in a protein. Remember, again we are not looking at the full structure here 3D, we are only looking at the 2D, I mean the secondary structure. Now, in the beta sheet it is little more long range, because these 2 strands can come together. So, let me show you this here. For example, in a parallel beta sheet, parallel means the sheets are parallel to each other, they are pointing in the same direction. So, when they come and fold like this, these 2 are actually very far away, these 2, I mean amino acid here and an amino acid here are actually very far away, but you can see that they are close in space because of this close hydrogen bond interaction. So, you can see the hydrogen bond are shown by dotted line. So, these NOEs, if you observe these NOEs in your spectrum, immediately you can conclude that this is a parallel beta sheet structure in that protein. Again, this is a local, it is a secondary structure. Remember, we are not still quantum to the tertiary, that is 3D structure. Similarly, this side, if you look at it, this is an anti-parallel beta sheet and the sheets are anti-parallel, the strands are anti-parallel. So, any 2 amino acid here, for example, like this, I am drawing by the red line, they could be far in the sequence, but they could come close in the space because of these hydrogen bond interactions. So, you can see this proton to this proton, for example, is a very characteristic of the beta sheet. This is also very characteristic of beta sheet. Means if you see the H alpha proton of one amino acid giving a cross peak or a correlation to H alpha of another amino acid, immediately you can conclude that there is a beta strand in that region. Okay. So, these are the type of signature which we get for beta sheet. So, now coming to how do we solve the structure, final 3 dimensional structure of a protein. So, what we do is we take all this distance information, remember we are getting the distance by from the intensity of the cross peak between the 2 atoms. So, these distances, all of these NOE intensities are converted to distances between the 2 corresponding hydrogen atoms. We call it as R, R means distance, Ij means between 2 atoms I and J. So, we call this as a constraint. Why? Because as I said, we are doing a model building here. Model building means we are trying to build a 3 dimensional model which is constrained by the distances which we are giving. So, our distances what we are giving is restricting the geometry, therefore, we call it as a constraint. Similarly, we also saw that we can get J values, J coupling, and from J coupling we can get the phi value. So, those constraint means those values are also given because we are constraining, restricting the geometry of the molecule. Then what is done next? Then next what is done is you start from a random coil structure. So, you can make this in a computer. You take a simple linear chain of an amino acid structure because you know the sequence of your protein. So, you build in a computer random coil structure which is done by software. Then you start at molecular dynamics calculation. So, this is something we cannot go into detail, but this is a computational technique wherein you start from a random coil and start giving the constraint meaning those numbers, the distances between the each amino acid to each other amino acid. So, all the distances which we get from nosy correlations are given as a input to this program and also the different angles. Then it carries out what is called as a simulated annealing and minimizes the energy of the structure, and finally it will give us a structure like this such that all distance and angle constraint or values that we have given are satisfied as much as possible. So, remember we are going to give thousands of constraints. So, typically for an 100 amino acid protein, the number of restraints which we give is a rough calculation is 100 into 15. So, about 1500 constraints. Okay. So, we are not talking about a few distances here, we are talking about 1500 distances and angles. So, obviously it cannot satisfy all of them to make a structure. There will be some distances which we give may be wrong in value. So, such cases it cannot do anything and it has to not satisfy. So, those are the one which we have to remove when we start. So, we have to refine this structure, we cannot keep on, it is not one step process. We get the structure, then we find some distances are violated means not satisfied, then we go remove those distance or we adjust the cross peak, maybe the assignment was wrong, so on so forth, and restart again and build a new model. So, like this we go iteration. So, I would say this process is an iterative, it keeps happening till we reach a level where we say okay, we are satisfied with the distances what and constraints that it has satisfied. So, that satisfaction once you reach, then we can say that our job is complete. Okay. So, but you recollect, if you recall in one of the slides I showed that if the distances are not sufficiently number, then there are a lot of uncertainties, means I do not know, for example, in this case where should I keep the B? B could be here, it could be here atom or this B atom, because I do not have CB and AB distance in my list, input list, this is the input list. So, therefore, when I am building a model to satisfy distances, and if I am missing distances, I cannot build a correct model, not correct model, I cannot build a unique model. So, all these three are possible, right, because I do not have any distance between these two. So, I have to consider all the three as equally correct, there is no distinction between these three. Therefore, in NMR what we are doing is we start from many different initial random coil structures, for example 100 of them, then all of them are subjected to the same energy minimization, and each time it will give me a different geometry or different structure, because each time it does not know to fit this B. So, sometime one structure may give me this result, another structure model may give me this result, another model. So, like that out of 100 I may get all different models. So, what I do is I will take the best 20 of the 100 which satisfy the distance. So, I will take the best. What do you mean by best? Best means where there is a minimum violation of distance. For example, if this is supposed to be 3, in some structure I may this may come out to be 3.6, then that is a big violation. If it is 3.1 it is okay, or 2.9, but if it is 3.5 or 4, then that distance was not correctly satisfied. So, I have to reject that particular structure. Okay. So, this is how structure building in NMR is done. So, this is how we, as we show in a publication or in a database, we show a bundle of NMR structures. We do not show a single structure like this, we show a ensemble, we use the word ensemble. Why? Because all of these structures which we have got, or there are about 20 here in this drawing, in this picture, all of them have satisfied the distance and angle constraints that we have given to the software. So, all of them are equally correct or good. So, we put all together and represent this. So, the average of this could look like this. Okay. So, this is, you can see already they all look same. So, as such there is no big difference, but I could take an average structure and show it as a representative model. Again we do not know the correct structure. So, basically this brings us to the end of the NMR structure determination. The last point here is we will come back to this in the next class, that we have to deposit these protein structures in the database when we publish, and we will look at this slightly in the next class before we move on to the next part of the course, that is protein ligand interaction.